Hi, Intensified Chemistry students. This is your Unit 6 lesson on the mole and mass. Now, in a previous video, we talked about the fact that the mole is a counting unit, just like a dozen. Just like 1 dozen is 12 of anything, 1 mole is 6.02 times 10 to the 23rd of anything. However, these two units, these two grouping units, are really appropriate for different things. 1 dozen is very appropriate for eggs or donuts because they are large, and basic idea is that, if you have a dozen eggs, that's a convenient thing to bring home. Now, a mole is convenient for something that is very, very small because that group is a large number of things. And so 1 mole is very appropriate for particles. And the particles we particularly work with in chemistry are atoms and molecules. So again, converting between moles and particles, you can use dimensional analysis. The conversion factor is 1 mole equals 6.02 times 10 to the 23rd particles, and we can write our conversion factors these two ways in order to decide whether or not we're going to multiply or divide the given by 6.02 times 10 to the 23rd. And remember, particles can either be atoms or molecules. So just to review from last slideshow, propane is a gas used for cooking. How many molecules are in 2.12 moles of propane? Again, you're going to see your given, and you're going to want to use the correct conversion factor. Pause the video here and see if you can do it, and then check your answer. Here's the answer. So here's our given. Our wanted was molecules. Remember, molecules are very small. That's our particle in this case. And so we can then line up diagonally mole and mole to cancel, and then this just becomes a multiplication. All right, here's example problem number 2. How many moles are in 4.65 times 10 to the 24th molecules of NO2? Now, again, let's find our given. It's this, 4.65 times 10 to the 24th molecules, and we're going to try to find moles. Notice this is a very big number. Molecules tend to be a very big number. Moles tend to be a much smaller number because we're trying to group things. Just like 12 eggs is a larger number than 1 dozen. Same thing, this many molecules should be a smaller number of moles because we've grouped them. So pause the video and see if you can set up the dimensional analysis correctly with your T-chart. So again, you are going to be lining up diagonally molecules. It leaves moles. That's what we want. We do this division. Be real careful with this because if you enter this wrong into your calculator, you can end up with a weird times 10 to the 47th, and that is just definitely not a smaller number. You're trying to group things. If you use your laws of exponents, you can essentially see that you're basically doing 46.5 divided by 6.02. In any event, you should have gotten 7.72 moles. Note, moles is a grouping number, so it's smaller than the original when you're going from molecules to moles. All right, example problem number 3, a little bit more challenging. Now it says how many atoms are in 0.75 moles of FeBr3. Notice it's asking for atoms, but our substance is a compound. FeBr3 is a molecule, not an atom. This means we need to add one more step in our dimensional analysis. Once we figure out how many molecules we have, then we have to look at how many atoms are in each molecule and multiply by that number. So in this case, we have 0.75 moles, and we start with molecules because these are molecules. We have 0.75 moles of these molecules. Notice how moles cancel. That intermediate step will leave us with molecules. But we notice in 1 molecule of FeBr3, we have 1 iron and 3 bromine, or 4 atoms per molecule. So again, you have to multiply by 4. That'll cancel out molecules. You're left with atoms. And again, rounding to the correct number of significant figures, this has 2. We usually match the given. This has 3. This is an exact counting number. There are exactly 4 atoms in 1 molecule, and that's why we don't worry about this being 1. This is actually infinite. All right, now we're going to talk about the mass. Now this is really convenient because we don't want to go around counting particles. That's really hard, and that's the whole point of a mole. you don't want to have to count out a mole of particles. You want to be able to figure out a shortcut to just being sure you have that number of particles. So the mass of a mole of any element can be found on the periodic table. The atomic mass of an element expressed in grams is the mass of 1 mole of the element, and it's otherwise known as the molar mass. So 1 mole of sulfur atoms, or the molar mass, is equal to the atomic mass in grams, 32.1 grams. A mole of mercury, again, you look at the atomic mass, 200.6 grams. So anything you see on the periodic table, the atomic mass is actually the mass of a mole, so we call it the molar mass. Now, the molar mass of a compound you're going to find by adding up all the particles. So, for example, this is a molecule of glucose. It has 6 carbons, 12 hydrogens, and 6 oxygens. If we figure out the molar mass of glucose, we have to add all of those together. 6 times the molar mass of carbon, plus 12 times the molar mass of hydrogen, plus 6 times the molar mass of oxygen, and you get 180 grams per 1 mole. Again, it's a lot easier to weigh out 180 grams of glucose than to try to count 6.02 times 10 to the 23rd moles of molecules of glucose. So it's a shortcut. We know if we have this many grams, we have that many particles. Same thing with water. Molar mass of water. 1 mole of water molecules. What is that? Well, I say 18 grams. Why? Because 2 hydrogens, if you look on the periodic table, each one is 1. So that's 2 times 1. And oxygen is about 16. So 2 plus 16 is 18. So if you have 18 grams of water, you have 6.02 times 10 to the 23rd molecules of water. All right, so calculating the molar mass, you substitute the unit grams for the atomic mass units, and thus 1 mole of SO3 has a mass of 80.1. So here's SO3, and it equals 1 sulfur and 3 oxygens. And as you can see here, to the 10th place, 1 sulfur is 32.1. The 3 oxygens to the 10th place are each 16. You add those all together, and you get 80.1 AMU. Now, when you make that mole, you just say it's 80.1 grams. So let's see if you can find the molar mass of AlNO3, aluminum nitrate. So step 1, you're going to determine the number and types of the atoms. Step 2, you're going to use your periodic table to find the mass of each element and multiply them by the number of atoms, and then you're going to add. So here you go. You have 1 aluminum, and remember the parentheses mean that you distribute. You have 3 nitrogen and 9 oxygen. So you can see here's the molar mass of aluminum. This time we're calculating out to the hundredths place. You'll just use whatever on your particular periodic table. We have 3 times the nitrogens molar mass and 9 times the oxygen atoms molar mass. If you add those all together, you get the mass, and this is grams per 1 mole. That's what this unit means. The molar mass of aluminum nitrate, AlNO3, is 213.01 grams. All right, let's try another one. Now this one's a little bit more challenging. There are these things called hydrated ionic compounds, and they are compounds that contain water molecules as part of their structure. So you have to add those in. The formulas of these compounds look a little bit different, and we need to include the water molecules as part of the molar mass. So it looks like this, and you see a dot here, and sometimes in math you think of that as being a multiplication, but it's not. It's just saying the whole formula for this hydrated, meaning having water in it, ionic compound, is this whole thing. And that dot actually means plus. So instead of having, so what you're going to do is you're going to find copper, you're going to find sulfur, you're going to have 4 oxygens, and then you're going to add the mass of 5 waters to it. So you're going to determine the number and type of atoms, and then you're going to use your periodic table to find the mass of each element, multiply them by the number of atoms, and then add. So for this one, 63.55 is the copper. Sulfur is 32.06. In case of oxygen, we have 4 here and 5 here. So that's 9 oxygens, okay? 16 times 9. So again, 4 from this formula, and since we have 5 waters, we have 5 oxygens. So that would be 9. And then 5 times 2, because we have 5 waters, that would be 10 hydrogens. And that would give you 10 times the molar mass of hydrogen atoms. You add those all together, 249.71. I think on the exit ticket you're going to be doing here, you're going to need this molar mass. So you might want to circle this so when you get to the exit ticket, you know this is the molar mass you're going to use. All right, now let's convert between moles and mass. Again, you can use dimensional analysis. In this case, a mole is whatever the molar mass is in grams. Remember, like 1 mole of water weighed 18 grams. So for water, it'd be 18 grams over 1 mole, or 1 mole over 18 grams. Again, we're going to cancel diagonally. So again, just like the conversions, you can go both ways. The mass is number of moles times the mass over 1 mole, and the moles is the mass times 1 mole over the mass in grams. Again, you can cancel units. Again, mass is going to be the big number. Moles is always a grouping number, so that it's going to be a smaller number. So let's try this one. What is the mass of 6.45 moles of aluminum oxide? You're going to have to find the molar mass of aluminum oxide first, and then you're going to have to set up your T-chart to figure out the mass. So let's look at that. Maybe stop, see if you can do it. So first of all, if we find the molar mass of aluminum oxide, it's going to be 101.96 grams. So 2 aluminums plus 3 oxygens should have gotten you 101.96 grams. That's the mass of 1 mole of this stuff. But we have 9.45 moles, so we will multiply 9.45 times the molar mass, cancel moles, and that'll give us 964 grams of the aluminum oxide. Again, notice, moles is the smaller number, grams is the bigger number. But in this case, if we wanted to have this many moles, and think about it, it's a lot of atoms to count, we wouldn't have to count them all out. We wouldn't have to multiply 9 times 4, 5 times 6.02 times 10 to the 23rd, and then try to count out those numbers of atoms. We would know we have that many atoms if we had 964 grams. Let's do one more problem. Example number 7. See if we get this. How many moles of Fe2O3 are in 92.2 grams? And again, we're going to have to figure out what the molar mass of iron oxide is. So 2 irons and 3 oxygens, and then set up our T-chart. Well, the molar mass of iron oxide to the 10th place should be 159.7, 92.2 grams, cancel grams, and so you'll notice that's not even quite a mole of iron oxide molecules. It's about half a mole. So again, the grams divided by the molar mass, again, these things have to equal. 1 mole of Fe2O3 equals that many grams, would be 0.577 moles. And that is your lesson on mass and moles and molar mass. And now you're going to want to go do your exit ticket.